Hello, this is Team BirdWords, and today we're going to be showing you our ESE472 Capstone demo. So our Capstone design is a mesh network intended to record bird and other animal sounds in forest environments, and then periodically upload this data to the cloud for scientific analysis. Now to start off our demo, we're going to be starting with Tyler, who's going to show you some of the hardware that we've been using.
All right, so the main component of our mesh network is what we call a remote sensing node, or RSN. This consists of an audio acquisition stage, a persistent storage medium, a microcontroller for processing, and a radio for transmission and reception. You may notice that our audio acquisition stage is missing, and this is because due to COVID-19, we were not able to share the hardware required for that. So for this demo, we're just going to be loading audio files onto the SD card, and we're going to be looking at the transmission through the network. So the remote sensing node is going to be sending packets of audio files over to this other XB. And the packets received are going to go into my computer, at which time they will go through an internet tunnel over to Omer's computer. So I think Omer's going to talk more about that now.
Thank you, Tyler. So once Tyler is sharing his file from his computer, meanwhile, you can see I'm SSHing to my Raspberry Pi, where I will be receiving the files. In here, the script for accepting the file from Tyler's computer, the tunneling script, is running on the background. It always runs when the Raspberry Pi starts. And here we can see the file received from Tyler, which would be encoded, will be received in this directory, which is empty right now. It will then be decompressed and will be stored in this directory, which is also empty right now. And finally, that file will be uploaded to the cloud in the Dropbox. We chose here Dropbox. It could be any other cloud if you want to. And the final file will be available here right now, as we will see in the end of the demo. Everything in here is synchronous and everything is timed. So if you want, we can change the timing later on. Now we'll go back to Tyler to start on the demo.
All right, thank you, Omer. I'm going to share my screen now. And you can see here on the SD card, we have this forest.flc file. So this is audio compressed using the flat compression algorithm. I'm just going to pop this out, move it over into the remote sensing node. We'll reset the microcontroller, and now we'll continue on screen. So we have a serial terminal open here. And this is showing messages received from the microcontroller. So you can see it starts up successfully. Now we're going to start the Python program, which is a tunnel. First thing that this program does is it performs network discovery. So this is where the coordinator node here connected to the master through the tunnel. The coordinator is looking for other nodes in the network, and this red indicates that nodes are finding each other. So after it finds the nodes, you can see here on screen it found RSN2. It's going to start sending commands to it. So first of all, this master coordinator node is going to be telling the remote sensing node to start recording audio. Then a short time later, it's going to tell it to stop recording audio. And then it's going to tell it to start transmitting the audio file over the radios. And the real bottleneck here is the radio transmission. These XB units that we're using support really very low data rates. So as we can see, this is taking a significant amount of time. But anyway, after the nodes are transmitted in this demo, after the audio files are transmitted, they are sent over the internet tunnel to Omer, and now Isaac is going to talk more about this tunnel.
Sure. So as we mentioned, due to the COVID-19 crisis, we were in a situation where our hardware was dispersed between our group members. So the idea that we came up with was a transparent internet tunnel, which would forward the packets from the mesh network transparently to the Raspberry Pi master node at Omer's house. So the way we're doing that is from Tyler's PC, these packets will be sent over a TCP connection, which is connected to Omer's IP address at a specific port that we decided upon beforehand. And now each message that we send across the tunnel will start with 4 bytes, which denote the ID of the node where the sound originated. So for instance, this could be RSN2, and that's used for the end user to determine which region of the forest the sound came from. And then that would be followed by 1 byte, which denotes whether it's the start, middle, or end of a packet, which is used by the Raspberry Pi as it gathers and assembles the packets. And then the remaining bytes would be, any number of them, would be the actual compressed audio itself. Now to speak a little bit about the compression algorithm that we're using FLAC, which is an open source lossless compression algorithm intended for audible sound. Now empirically through our tests, we found that the compression algorithm achieved a compression rate of around 2/3, meaning ultimately our final compressed file was 2/3 the size of the original. And the FLAC algorithm comes with 10 different levels of compression. Empirically, we found that higher levels of compression did not significantly reduce the size of the end file, although it did significantly increase the time that it took to compress the file. And now I'm going to be returning back to Tyler to speak a little bit more about the hardware.
Sure. So if we look on screen, we can see that we are receiving messages from the embedded systems right now, just this NS equals a certain number. And this is indicating how many sectors of the audio file have been read from the SD card. So we read from the SD card in four sector chunks. Each sector is 512 bytes. We then packetize these chunks that we read, and we send them over the radios. So once it reaches number of sectors equals 952, that's just what we know from sending this particular file. The transfer will be complete, and we can go to Omer to see what's happening on his end.
So as Tyler is sharing screen, you can see his screen, and you can see on the left side my console. And here we can check. We can see finally the FLAC extension is here in the RSN2, and so the file is here, so we can check if the decompression is done. I see we're still waiting for decompression. It usually takes a minute at most, so it should be done at any time. Meanwhile, we can check the Dropbox that is still empty. If Tyler wants to say it, okay. So meanwhile, we have to give it not too much time for the decompression to happen.
Just while we're waiting, I'm going to pipe in to say that we can see that the whole process of acquiring and transmitting audio has repeated in the background. This is because when there's a large number of nodes in the system, we would want to go through each one individually to send their audio, but we only have one node for the demo.
Meanwhile, we can see the decompression is finally done, and we can see that RSN2 is available here with the WAV file here, and we can hear the WAV file right now if you want to. So here we heard the WAV file, and we can see the bird noises there, which can later be used as the scientists want to be. So thus we conclude our demo in here right now. Thank you for watching.
Thank you.